Hello. Hello everyone. My name is Sneha. I'm working as an applied machine learning intern as part of the AI engineering team. My topic for this internship was interpretability within vision language models. So I'm going to talk about that. So this will be the outline for today's presentation. First, I will be going over why this research is happening, what's the research idea, and then some experiments we have conducted so far, like BCos integration and automated concept extraction. So talking about the motivation, why exactly are we doing it? Like there are a lot of existing methods for post hoc interpretability or for inherent interpretability. So why exactly this research is taking place is because of the limitations of the existing methods. For example, the post hoc interpretability methods have like what happens is as part of post hoc interpretability is basically the model already makes the decision, and then the explanations are generated for why that decision was made. This has a lot of limitations or problems, I would say, like the faithfulness is an issue. Like the explanations may not reflect the true reasoning of the model because the heat maps that are generated often have often highlight irrelevant or spurious regions. Apart from that, and because of that, uh, there is like limited trust on it in the clinical usage. I mean, doctors can't like rely on some saliency maps that are not that much helpful in understanding how the decision was made from that model. So because of that, we thought of coming up with this idea. Okay, let's make the models interpretable by default. So while the post hoc interpretability is good, it's easy, it's flexible, it's easy to integrate with the existing black box models, but making the models inherently interpretable basically improves the faithfulness of the model, and it also basically gives you more idea. Like it also like helps with the decision making, and it also gives you some idea, and it also provides human to have some control over the model. So the diagram here is actually the base model on which our research idea is based. So this is known as a concept bottleneck model. So what happens as part of the concept bottleneck model is like you basically add a concept layer. So instead of having a mapping from the input to output, you have a layer in between to basically see what are concepts were used to make a final prediction. So because of this, what happens is like the basically the end users or the radiologists or the doctors can actually change the concepts which are being shown by this layer, and which is known as human in the loop, which will give them power to basically control the end decision or change any wrong concepts that are being highlighted in the concept layer. So that is a brief about the idea. Yeah, so this is what I was talking about. The concept bottleneck models have input to concepts model, and then you have the concepts to the final label prediction part. The benefits of this, as I mentioned before, is like what if reasoning, which is just the human in the loop part, like human have control over how they want to change the concepts for the final prediction to change. And that is also like bridges the black box models in the human understanding part, like I explained. So yeah. Okay, talking about the research idea or the focus of this internship, or what are we trying to enhance as part of the model that I just described, is there are a lot of issues with the existing concept bottleneck model, such as the list of concepts which are being shown by the concept layer. You need to have them annotated beforehand itself. Which is kind of expensive because you need some domain expert to do that for you. And the other issues are like there is no visual grounding of the concepts. Like you can't view where exactly in the image that concept is present. Apart from that, there is no hierarchical or graph-based organization of concepts. Like all the concepts predicted by the concept layer are flat concepts, which is an issue, especially in the medical domain, because in the medical domain there is an anatomical structure which is being followed and then the final prediction is made. So, and also like the concepts are related to each other. For example, if I talk about chest X-ray images, you can have concepts like left pleural effusion, right pleural effusion, and those are like related, like they can be easily organized in a graphical format. Then the other issue is that the first model, which do the input to concept mapping, is again a black box model. Like a normal convolutional neural network is being used for that purpose. So we are like trying to make it more interpretable by replacing it with some inherently interpretable model. So this is the first experiment which we conducted, as part of which we tried to solve the problem of having a black box model for the input to concept prediction part. So we tried replacing the normal CNN model with a BCos network. What happens as part of BCos network is that they replace the linear transformation by BCos transformation. BCos transformation is nothing but like the linear transformation is like basically it just gives you the linear output, like it just like calculates the weight into the input part. So what happens as part of the BCos transformation is you add a cosine similarity score between the inputs and the weights to the power b. So b is a hyperparameter which you can adjust to basically like enforce that input to weight mapping. So the higher the b is, the higher the stronger the mapping is between the inputs and the weights. So yeah, that's what makes the BCos networks inherently interpretable at the output. If you basically plot the weight metrics for that network, then you can see the exact features which ultimately resulted in the label, like in the output prediction for the specific image. So we also use the BCos network because if we can get something like this in the output, then we can easily show, like we can have a bounding box on top of it and we can show as to where the concept is exactly located in the image. So that was the idea. So there are, like in the CBM model, there are various ways to train it, like independent, sequential, and joint. So in independent, you basically train the two networks independently. The X2C and C2Y, input to concept and concept to label prediction, happens independently, while in sequential, you basically do it in a sequence. And in the joint one, you do both C and Y, X2CY, jointly. Like the loss is different for each of these training methods. So we actually dealt with the joint training paradigm here mainly, and we also replaced the vanilla CNN with the BCos ResNet 18 model. So these are the results. We did some extensive experimentation for this part because the model didn't give us the output as we anticipated. So that's why we ended up doing a lot of experimentation for this part. And the best performing model was the one which we got from joint training after training for 399 epochs. And these are the losses, accuracy, and the other parameters. So this is what we got after from that best performing model after replacing the CNN, vanilla CNN with the BCos network in the CBM. So as you can see, we are able to like get some idea as to what, where exactly that object is present inside the image after using the BCos network. But after replacing the vanilla CNN with the BCos network, but there was still some issues, like the concepts which are being used here aren't located accurately. Like for example, for the beak, the wings is being depicted in the final image, and issues like that still exist. This is another image showing the same. So here, for each of the concepts, they are slightly blurred out, but yeah, for each of the concepts, for this 3, it's still correct. The concepts that are highlighted in green are the ones for which the image depict the correct area where that feature should be, but for the red ones, it's wrong. So it's like 50-50 wrong and correct. So what we did is like we instead moved to a CVM variant known as spatial CVM, and we are trying to like do some research on that part if we can still improve it, or else if we can do that part using some another inherent interpretable model. The next part was the automated concept extraction part. So as part of this, there were 2 main ideas. Instead of having an expert annotate the concepts for you, we can either generate those concepts using a RAG-based system, or have an agentic pipeline, agentic flow in place to do the same for us. So as part of the RAG-based concept extraction, initially we had used GPT-4, but because of the cost part associated with accessing the OpenAI API, we ended up moving to the open source models like Llama 3, Med42, etc. So these are the results for the different models that we tried. The first one was all this results are computed for the 100 to 150 images from the Mimic CXR, taken from the Mimic CXR dataset. And we use the reports, radiology reports present as part of the dataset as context to the LLM part. So with the GPT-4, like after calculating the concepts, this graph was generated by passing those concepts along with the images to a vision language model, which will basically give us the similarity score between the concept and the image. This is useful to find the visual features rather than the textual features, which will be more useful to the radiologist or end users for basically seeing what features have been used to make the final prediction. So these are the top 30 features, and the minimum similarity score which we got from the VLM was 0.35, 39, while the maximum similarity score was 0.42. Then this is like a brief comparison of what different open source models were used. So we ended up using like 3 medically fine-tuned models, while one is the generic Llama 3 model, this one. So in this case, the medically fine-tuned Llama 3 model ended up giving the best results. In our case, the BioGPT wasn't that useful because, first of all, it's not instruction tuned. It's a conversational model, more like a conversational model. So it cannot produce it can not follow the instructions properly and produce some JSON output. It is weak at the structuring part, and it was also released. It's a very old model. It was released before the instruction tuning became widely used. The other models like OpenBioLLM didn't work because, again, it's not instruction tuned, so it was producing very weakly organized concepts, and the concepts were very long because it is produced to trained to produce text only output. The other model was the Llama 3 model and the Med42. So the Med42 is an instruction tuned model, and that's why it's performing better compared to the other models. So these are the results using the Llama 3 models, the top 30 concepts, and the highest similarity score was 0.44. And in this case, it was 0.43, but most of the extracted concepts passed the 0.4 threshold in this case. So, yeah, sorry for that. So the last part is the agentic pipeline. So as part of this, so this is like a brief of the agentic flow architecture. So here we are planning to use two different agents, and then there is a critic model. So and these are the models, the LLMs and VLMs we are planning to use as part of those functions or agents. And this is the agent state that we have decided. Due to time limitations, I won't be going in much depth here. So the high level idea is to basically replace the concept extraction flow with this pipeline in majority of the papers, because majority of the papers have just used an LLM and they're just calling that for getting the concepts. So yeah, that was a brief about what we are planning to do. The next steps are obviously to do the visual grounding of the concepts and to organize the concepts into an hierarchy, because our focus is mainly in the medical domain. So for this research, so thank you.
Did you compare the performance of the CVMs to just the pure black box model? Like, how much, like if you were to like pick the state of the art model for like, I don't know, predicting like pneumonia or whatever your data set was predicting, and then compare that to a CVM, I presume you lose some performance by enforcing that bottleneck? Like, what's the trade-off?
Yeah, so definitely we do lose some performance. So first of all, giving some idea of our data set, it's the Mimic CXR data set. It has 14 classes, and we are using the CVM and all those models for that. So the best performing model in case of CVM was the one with the ResNet 18 backend for the concept prediction part. So there is some performance degradation, but in case of CVM, it's not a lot. Like even the paper defines that there is not much accuracy drop when they introduce the concept earlier in that end-to-end network, and they have like shown some results. And even we noticed that when we replace it with the BCos network, there was not much performance degradation. The issue was the images are not correct.
So my question was more, if you use a CVM to predict your 14 classes, where you're enforcing that there needs to be like some concept in the middle, right? As opposed to just using, let's say, the state-of-the-art model for that data set is ResNet with no concepts. So just a complete black box model. Is the complete black box model higher performance? Like, do you lose performance by forcing that there needs to be this concepts essentially? Do you lose performance by adding explainability?
Yeah, so as I mentioned, we were not losing that much performance. Like we did conduct those experiments, and the performance drop was like around 1 to 2% something. So I believe it's not a lot in comparison to what we are getting, like the concept. So yeah, that's why we ended up sticking to it.
There's one. Thank you.
Yeah.
Good morning. Yeah, so actually I'm just curious about there is how is the trade-off between interpretability and efficiency of the model, right? So I'm just curious about what are the minimum and maximum permissible limits for that. So okay, on the one hand we make the model more interpretable, but we lose some performance. So do we have max cap for that? Is it well defined in the iteration?
I'm not sure if there is a maximum cap over how much accuracy drop is allowed, but with the specific kind of models that we have been focusing on, there hasn't been like I mentioned, there hasn't been like much performance drop. Like it's just 1 to 2% when we did the end-to-end, and I think as part of the experiments also I have mentioned in the table. So there was not like much performance difference between the standard model. This is the standard model, and the other ones are the CVM models. So for the X2Y training, for the input to output prediction, there was not much performance loss, and even like the human in the loop part actually ends up improving the performance, because you give radiologists the control to change some concepts based on if they feel they are wrong. So that ultimately helps in improving the performance as well. So because of these reasons only we ended up using the CVM, but mainly because of the human in the loop part, and there was not much performance drop as well. So yeah, I hope I was able to answer the question.
Yeah, thank you so much.
Thank you.